Now, I am going to skip property number 5 and I am going to come to what is called the property of convolution, one of the most important results of the discrete time Fourier transform. So, I am going to put a double star on this one because this is going to be a very, very important result, a very powerful result, and something that you must always be able to apply, because it's a very important result. So, let us look at this result and see how we can derive that. So, the convolution theorem, which is property number 6, convolution theorem, can be explained or can be written down in the following manner. If you have two sequences with the discrete time Fourier transform given as below, x of n with discrete time Fourier transform x e of j omega, and an impulse response h of n given by h e of j omega. Okay, the common place where we will encounter is an input x of n and a discrete time LTI system. Discrete time LTI system, which is denoted by means or characterized by means of its impulse response, then the output y of n will be equal to x of n convolved with h of n. Now, y of n will have a discrete time Fourier transform which is given by y e of j omega. Now, the question is, how is y e of j omega related to x e of j omega and h e of j omega? So, that is again a very, very important result, powerful result. So, let us see if we can derive that. So, y of n is equal to x of n convolved with h of n. Okay, this is given by summation k equal to minus infinity to infinity x of k h of n minus k. We have time reversed the impulse response and we have retained x of n exactly as before. Okay, so our desire is to get an expression for y e of j omega, that is equal to summation n equal to minus infinity to infinity y of n e power minus j omega n. We will substitute for y of n. So, this is equal to summation n equal to minus infinity to infinity. I am going to substitute for y of n, summation k equal to minus infinity to infinity x of k h of n minus k and then e power minus j omega n, e power minus j omega n. Okay. Now, I am going to do a simple change of variable. L is equal to n minus k. Okay. K is, if you think of k as a constant, when n goes from minus infinity to infinity, L will also go from minus infinity to infinity. So, substitute for this will become summation L equal to minus infinity to infinity, and what we will have here inside in the inner summation, it will be k equal to minus infinity to infinity x of k, remember h of n minus k now becomes h of L e power minus j omega, n will be equal to L plus k, okay, basically just a substitution. Now, grouping of terms, all the L terms together, L equal to minus infinity to infinity, h of L e power minus j omega L. Group all the x terms together, k terms together, k equal to minus infinity to infinity, x of k e power minus j omega k. So, this second term is nothing but x e of j omega. The first term is h e of j omega, giving us an extremely powerful result which says if I convolve x of n with h of n, then I get a discrete time Fourier transform which is given by xe of j omega he of j omega. Okay. Why is this result so powerful? Remember, we said ideal low pass filter. Ideal low pass filter, okay, h of n. Okay, now again you will have to help me. What is the expression for ideal low pass filter? We wrote it in terms of the sinc function, right? Okay, so I will let you write it down. Okay, so convolving the input x of n with an ideal low pass filter. Okay, ideal low pass filter is infinitely long, two-sided, lot of things. So the time domain does not give us much intuition into what happens with low pass filtering. On the other hand, if I were to look at the frequency domain, if this is xe of j omega, mod xe of j omega, and the ideal low pass filter is here, this is he of j omega, ideal low pass filter. The product of these two then says what will be the result. The resultant will be the convolution in the time domain did not give me much of an insight, but on the other hand, the frequency domain representation gave me a beautiful insight which says that all frequencies above omega c will get eliminated, and that will be the, so this will be minus omega c to omega c, and this will be the new spectrum that is at the output. So the convolution in time translates into a product of the discrete time Fourier transforms, and this is extremely powerful result and something that we will use time and time again in our understanding. Let me give you one simple example. If you remember, we said that there is a discrete time system, we called it a delay d, which will produce for me an output which is x of n minus 1. Okay. We said that this is equal to xe of j omega, and remember we said time shifted expression e power minus j omega xe of j omega, correct? Okay. Now, if you remember, we had derived the impulse response of a delay. Impulse response of a delay is delta of n minus 1. The delta occurs not at n equal to 0, it occurs at n equal to 1. Why is this true? Because x of n convolved with h of n is the same as x of n convolved with delta of n minus 1, which will give you x of n minus 1. Correct? That is what we got from the time domain expression. Now, if you were to do the discrete time Fourier transform of this, what will he of j omega be equal to? A delta function occurring at n equal to 1, so only one term in the infinite summation, it will be 1 into e power minus j omega. Okay, so basically e power minus j omega. So what is the output? The output of the two functions is using the convolution theorem. Using the convolution theorem, what is it? It is x e of j omega, h e of j omega, which is the same as x e of j omega times e of minus j omega, which is what you got when you took just the expression, the discrete time Fourier transform of x of n minus 1. So basically you can get it from impulse response, you can get it from the property of a delaying of the input signal, you can also get it from convolution theorem. So all three will basically be consistent, they have to give you the same result, and therefore this becomes a very powerful framework for us to obtain and to work and to work with this. Okay. So now let us look at one more way of verifying the convolution result. So the convolution theorem, this is proof number 2. Proof number 2. Okay, so just like before, we have this expression n equal to minus infinity to infinity, and inner summation which is k equal to minus infinity to infinity, x of k h of n minus k e power minus j omega n. Okay. Now, I am going to rewrite this expression. Okay. So, I am basically going to interchange the order of summation and integration of the summation. So, this is going to be summation k equal to minus infinity to infinity, summation. So, I can bring the k out, x of k out here, x of k. This is n equal to minus infinity to infinity, h of n minus k e power minus j omega. But for this to be like a discrete time Fourier transform, I am going to add and subtract one term. Okay, so I am going to do omega minus k. That means effectively what you will get is e power j k, right? So, is that what? One second. E power j. Sorry. E power j omega, and I will do n minus k. Sorry. N minus k. So, because I have added a minus k term, I also should take care of that. So, there will be a e power minus j omega k. Okay, so I hope, so basically I have added and subtracted an exponent with the e power j omega k. So, this inner summation becomes same as h e of j omega, and then what we are left with is summation k equal to minus infinity to infinity x of n x of k, sorry, x of k e power minus j omega k, and this of course will be is x, this is x e of j omega. Okay, two ways in which we have proved the result, and you can utilize this in a very powerful way. Now, moving on, if you look at the table that we have been working from, so we have proved several of the important results. Now, there is another so convolution in the time domain gives you multiplication in the product in the frequency domain. Now, the principle of duality holds where multiplication in the time domain will give you convolution in the frequency domain. Okay. Now, we have to be a little bit careful because we are now dealing with periodic functions. X e of j omega is a periodic function, y e of j omega is a periodic function. When you want to convolve them, you must do what is called periodic convolution. Okay, we will explain that in a moment. But the important thing to note is that the counterpart is also true. Multiplication in time, convolution in time gives you multiplication in frequency. Multiplication in time will give you the dual where you will get convolution in the frequency domain. So, this is a very powerful result. But before we get to this particular the multiplication property, let me introduce for you a very powerful result which is called Parseval's theorem. This is something that you would have studied in signals and systems. This is there even for continuous time signals, but let us look at what is the corresponding result that we have for discrete time signals. So, Parseval's theorem. Parseval's theorem says that if I have a discrete time sequence x of n whose discrete time Fourier transform is given by x e of j omega, then we know that the energy of the signal can be computed in the time domain using the expression n equal to minus infinity to infinity mod x of n magnitude squared. Okay. Now, Parseval's theorem says that you can also compute the energy not only in the time domain, but you can also compute it in the frequency domain. Now, in the frequency domain, remember it's the discrete time Fourier transform is a periodic signal. So, you do the energy computation over one period, 1 over 2 pi minus pi to pi mod of x e of j omega whole squared d omega. The discrete time Fourier transform magnitude squared integrated over minus pi to pi is going to give us the result that we are interested in. Okay, so let us do a quick proof of this particular result. So, on the left hand side we have n equal to minus infinity to infinity x of n x conjugate of n. Magnitude squared can be written as x of n conjugate. Okay. So, if you remember, we wrote down the expression for x conjugate of n. So, in the following manner, so we will get summation n equal to minus infinity to infinity x of n. The discrete time Fourier transform of x conjugate of n can be obtained as x conjugate of n. I am writing down the expression 1 over 2 pi minus pi to pi x conjugate e of j omega e power minus j omega n d omega. Okay, so this is, I have basically written down the expression that we have for x conjugate e of j omega. All right, I hope you are comfortable with this. Basically, you write down the expression in case you are wondering, you know, there seems to be a minus sign there. What is the expression for x of n? 1 over 2 pi minus pi to pi x e of j omega e power j omega n d omega. So, if you conjugate, you get conjugate here, you get conjugate here, you get a minus sign there. That's what is the expression that we have. Now, interchange the summation and integration, you get 1 over 2 pi integral minus pi to pi. We can take the x conjugate e of j omega outside. So, let me do that. Minus pi to pi x conjugate e of j omega, take the summation inside, summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay, and of course there is a d omega. Now this is nothing but x e of j omega. So what we get here is 1 over 2 pi integral minus pi to pi magnitude x e of j omega magnitude squared of d omega. Okay. So this is Parseval's theorem. You can compute energy in the time domain or you can compute energy in the frequency domain. You will get exactly the same result in both cases, minus infinity to infinity x of n magnitude squared. Now, one common mistake students will make will say that this is the discrete time Fourier transform. Now, Parseval's relationship is not a discrete time Fourier transform. It is a computation of the energy. So, this is not the arrow that shares it's a discrete time Fourier transform. It's actually equal to sign. So, you can compute it in the time domain or you can compute it in the frequency domain, you will get exactly the same result. So, this is an equal to sign, not a transformation sign. Okay? So, that is very important to note. Now, what I would like you to do is to verify the generalization of the discrete time Fourier transform, the Parseval's theorem. The Parseval's theorem, where we compute a form of correlation x of n y conjugate of n, n equal to minus infinity to infinity. So basically it's a type of correlation that we are doing. This can be written as 1 over 2 pi, again multiplication in the time, convolution in the frequency domain is a minus pi to pi x e of j omega y conjugate e of j omega d omega. Okay, I would like you to verify this result, and of course if you substitute y equal to x, you will get the original version of the Parseval. So basically this is the generalized Parseval's theorem, and this also finds a lot of good use in the expressions that we had. So this is generalized Parseval's theorem.